Let's give you a quick review for previous class. Actually, previous class we talk about we finished the first section and talking about the thermally activated diffusion process. So based on the quantum mechanics theory, we can estimate the atomic jump rate associated with atomic vibration frequency times the probability of crossing the barrier. Related to vibration frequency, this term actually is correlated with bond strength between atoms, and also the reduced mass actually is the mass of the atoms. And the second term related to probability of crossing the barrier depends on the energy, the thermal energy, which atoms have. So as long as the atoms has energy higher than energy barrier or migration energy, then the atoms can make a successfully jump to surrounding available size. So this term will be related to the energy barrier and also the surrounding or working environment, temperature of environment. So now we know the successfully atomic jump, and as you know, diffusion, which we observe in macro scale, actually is a result of series of atomic jump process. So in order to give you a quantitatively description between the diffusion and atomic jump, we use the randomly work process as an example and demonstrate that find a good indicator to describe the diffusion phenomenon, which is mean square displacement, capital R. And the first method to obtain the mean square displacement we used is the spreading of a point source. Then after series deviation, then you get the mean square displacement equals to 6 times diffusivity times diffusion time period tau. And the other approach to obtain the mean square displacement is through calculating the radial probability term to get the mean square displacement, right? And after deviation based on the one-dimensional models, then we can get the mean square displacement equals to total jump rate times diffusion time period tau and mean square jump distance. So we equal these results, then we can get a beautiful relationship. Is the expression of diffusivity equals to total jump rate times the mean square jump distance divided by 6. But this results can only be applied in random work process. In order to broaden the usage of this equation of diffusivity, then we modify these results by an addition of one factor, which is we call it a correlation factor. So after ending this term, we got the expression of diffusivity equals to gamma mean square jump distance times correlation factor F. F, don't forget that F equals to 1, which is the same with this results, right? It means we are talking about the random work process. If F correlation factor equals to 0, that means what? The atoms jump back and forth, right? And this kind of phenomena is nothing related and no contribution to the diffusion phenomenon. So while F equals to 0, actually diffusivity equals to 0. As we mentioned, the atoms jump back and forth. And we also, in previous class, we also tell you how to roughly estimate a value for correlation factor, right? And you can check that from previous slide. Okay, so following slide, we are going to use these results to further calculate the diffusivity in different crystal structure through different diffusion mechanism. So let's move to section 2, diffusion in crystal lattice. So how atoms jump in crystal lattice? First of all, we are going to introduce you 4 different diffusion mechanisms in crystal structures. And this part, we also give you some examples, but here the materials we will focus on will be the metal materials. And in the second section of second part of the sections, we are going to talk about the atomic diffusion in ionic solid. How can we deal with when the diffusions happens in ionic solids? So let's move to the first sections. We are going to introduce 4 different diffusion mechanisms. In previous class, we already introduced the ring mechanism and also the vacancy mediated mechanism. What's the ring mechanism? Actually, is our diffusing atoms exchange with a site with surrounding host atoms in the meantime. That means the diffusing atom jump to right and the host atom jump to left. So they move together. So this will cause the high lattice distortion. So that means the energy barrier is high. And as long as, because the energy barrier is high, so it only can observe in high temperature. And in order to lower the lattice distortion, some people probably will observe more atoms move together. That means more atoms move simultaneously. But as you know, the probability of the atoms to move together is quite low. So this is what we call a ring mechanism. And what's the vacancy mechanism? Vacancy mechanism means the diffusing atoms is going to jump into surrounding available vacancy. So as you know, which parameter factors will determine this the diffusivity of this diffusing atom would be the concentration of vacancy and also the migration energy of the atom. So as you know, the concentration of vacancy is proportional to the vacancy formation and exponential minus vacancy formation energy divided by kT, working temperature. And regarding to the atomic migration energy, we can, as we know, mobility of the atom is proportional to migration energy minus exponential minus migration energy divided by kT. So when we talk about the diffusivity of the materials through vacancy mediated diffusion process, the expression of diffusivity is proportional to exponential minus energy minus energy term included the vacancy formation energy and migration energy is like times this. So it's vacancy formation energy and migration energy. So activation energy part shows included the vacancy formation energy and migration energy. So we give you an example is if we have a vacancy mediated self-diffusion in FCC. So this is FCC structures, and you can see the vacancy at the center phase. And we just directly use the results we derived in previous section is the diffusivity equals to atomic jump rate gamma mean square jump distance divided by 6 times the correlation factor F. So based on this result, you can simply get or formulate the 2 diffusivity. The first one is self-diffusivity of the atom, and the second diffusivity is the diffusivity of the vacancy. So based on the self-diffusivity of the atom is you can just gamma, you use the atomic jump ray and label with A means the atoms for atoms, and R squared divided by R is a small r is the nearest distance allow the atoms to jump into the vacancy, so it's a small r, and use the same idea to get a diffusivity for the vacancy is the atomic jump ray for vacancy, the small nearest distance of vacancy to jump into the lattice point or exchange the location with atoms is a small r squared. So, and we know the nearest distance, small r, right, is this distance. So you can just a squared, take a root of it and divide it by 2. So you got the nearest distance between the vacancy and the atoms. And as you know, so now we know the small r, right? Then in order to know the total jump rate, so you need to determine the z. For the z in FCC actually is, for this vacancy, the nearest atoms, how many nearest atoms toward to this vacancy would be 12, right? This 12. So you can use the z equals to 12 and r equals to this and substitute this equation. You can get the gamma A prime is an atomic jump rate in specific directions. A squared is a lattice constant for this FCC and F correlation factor. The same results you are going to get is the gamma V prime, right? Because gamma also for the vacancy only there are 12 available sites to allow this vacancy to exchange with the atom location with the of the atoms. So you will get the same results here, but then next step would be we need to know the F for the vacancy. Vacancy can jump in anywhere, right? Anywhere, I mean, can jump either this here, this, or this to vacancy. There's a uncorrelated or random walk, right? So F equals to 1 because vacancy can exchange with the location with any atoms, any nearest atoms, any one of the atoms out of 12, right? So F equals to 1. But if you consider the atoms cannot jump. Atoms can only jump to where? To nearest. Atoms cannot. Atoms only can jump as long as there is a nearby vacancy surrounded it, right? So F is not equals to 1. It will be the correlated jump. So we need to, and the F, we cannot, the F won't are not equals to 1. So we need to leave F here. And next, we need to think about what's the relationship between the gamma A prime and the gamma V prime. Atomic jump rate in specific directions to atoms would be limited by what? The atomic jump rate will be limited by the concentration of vacancy and also the vacancy jump rate in specific direction. So gamma A prime will be equals to XV gamma V prime. So after that, you can get the relationship between the self-diffusivity of the atom and the diffusivity for the vacancy can be expressed like this, because it's a D star self-diffusivity, right? XV and this one is dV times F. So based on this, you know the self-diffusivity of the atoms in FCC equals to atomic fraction of vacancy, diffusivity of a vacancy, and correlation factor F. So as we mentioned in previous class, you know the dV must be much higher or larger than self-diffusivity D star, right? Because usually XV is very small. So based on lecture 2, if it is a thermal equilibrium conditions, you can get the atomic fraction for vacancy will be equals to exponential minus vacancy formation energy divided by kT, and G can be separated into H minus Ts. So you can separate into temperature independent term and temperature dependent term. So you can rewrite the self-diffusivity becomes to XV dV. What's the next is dV, right? dV is a gamma V prime A square. Gamma V prime is a vacancy jump rate can be expressed like vibration frequency times the probability of crossing the energy barrier. So dV can be expressed like this. And you also times the A square here, and we left F here. So here you can separate them into two terms. The first term is the temperature independent term, and second term is temperature dependent term. And this is entropy, this is enthalpy. So here you usually in previous textbook or when you learn the diffusivity in material science and engineer books, you will always you can see this kind of expression for self-diffusivity equals to D0 exponential term, right? And what's the D0 means? Or what's the factor? What's the D0 here? Actually, after series deviation, you know D0 actually included the correlation factor F, lattice constant, vibration frequency, and also the exponential entropy term. And the second term related to temperature is temperature dependent part. Actually, the energy is enthalpy term, and this energy part included the vacancy migration energy and vacancy formation energy. Okay, so as we mentioned before, you can measure or you can do the experiments to measure the energy term in your materials, of your new materials. How to do that? As long as you measure the self-diffusivity of the atom at different temperature, for example, like at 5 different temperatures, then you make a plot of log D star versus 1 over T. Then after fitting the slope, you can get the E. So you know you can estimate or you can measure or estimate the energy term of your materials experimentally. And next slide is going to show you how to determine the vacancy formation energy and migration energy of your materials. So we assume it is under the thermal equilibrium condition. Then the vacancy atomic fraction can be expressed like this, right? And it's the numbers of vacancy over the total numbers of atoms. And as long as you heat your materials up, then you can observe the thermal expansion. So you can get the delta L over L. And the thermal, as long as you heat your materials up, the thermal expansion included two terms. The first term is the increase of numbers of vacancy, and the other one is the increase of lattice constant. So you use the thermal expansion term minus the contribution from the increase of lattice constant, then the residual part will be related to the increase of the numbers of vacancy, and how to measure the increase of lattice constant. You can by XRD. Then this is the length, right? In one-dimensional, so usually we will times 3 to become the 3-dimensional term. Then you can get the this will be equals to XV is a vacancy fraction, vacancy atomic fraction. And as we mentioned, how to do that? Yes, you know this value, right? At certain temperature, so you can measure XV this for phi temperature, then have a log on this equation. So after fitting, you also can get the slope. The slope is corresponding to vacancy formation energy, this one, vacancy formation energy. And the intercept for log this value will be associated with the entropy term. Okay, so as long as you know the vacancy formation energy in these materials, and and you know this vacancy formation energy for your materials, right? And in previous slide, we show you that actually you also can know the energy term by measuring the self-diffusivity at different temperature. Then you can get this term. So this minus this one, when you can get the vacancy migration energy of your materials. So this is how we can determine the vacancy formation energy, vacancy migration energy in your materials. Okay, so let's move to the third part, is the interstitial mechanism. Interstitial mechanism is much simple compared to previous one, because the diffusing atoms is the small solute atom, and this atom diffuse through interstitial sites in your materials. So when you write down the diffusivity, the expression of diffusivity of this solute atoms is proportional to exponential minus energy term is only the migration energy. This term only related or associated with the lattice distortion during diffusion of this atom, or during the atomic jumping process of these atoms. So, and as you know, if we take the BCC as an example, then there are two different interstitial sites. The first one is, we call it the octahedral interstitial site, and we label that in small white ball. And we also have we call a tetrahedral interstitial site in BCC. Here we label it also in a small white ball here. So if we assume now we have BCC materials, and there's an interstitial diffusion observed in or happened in these BCC structures, then through the octahedral interstitial site. So first of all, you need to draw the unit cell of BCC, and because the solute atoms diffuse through octahedral interstitial site, so next step you are going to label all available octahedral interstitial site. Then in order to estimate the diffusivity of this solute atom, then we just grab the results here, and based on the results, we just identify each terms. Then you can get the diffusivity of the solute atom. So I try to make a simple figures here. The BCC, we assume the lattice constant is A equals to A equals to A equals to B equals to C. So we use the A is a lattice constant, and interstitial. So we focus on this octahedral interstitial side. And as you know, if you focus on this plane, then how many available possible jump directions to this interstitial the interstitial atoms is 1, 2, 3, 4, right? Only can jump either here, here, there, here. It's not going to jump here because this is the distance between this interstitial side is longer than this one. So the interstitial atom only can jump to the nearest available interstitial site. So will be only 4 possible directions. So here is 4 gamma prime. Gamma equals to 4 gamma prime. So we use the I to label that this diffusivity is interstitial diffusivity of the solute atom. So it's a 4 gamma prime, and the small r is the means the distance of each jump. So the distance here is a over 2. So take the square of it. So it's a squared over 4. And for interstitial atoms, it can jump anywhere. It's nothing. This jump is nothing related to previous or next jump. So f equals to 1. So you can simply get the after arrangement. You put the temperature independent term here and temperature dependent term here. So we can get the D0 is here, and the second term is exponential term. And as we mentioned, the energy E here is enthalpy is only related to the migration energy, which is associated with the lattice distortion energy, right? Okay, so let's give you an example. If we have the ion BCC structures, and there's a solute atom is a carbon atom, and carbon is going to diffuse through octahedral interstitial site in ion materials, BCC ion materials. Can we measure the D0 and the migration energy of these materials? Can we do that? Measure that. Can you design experiments to measure the D0 and HM? Yes, you can do that, right? As long as you measure the diffusivity of this carbon at different temperature, for example, like at 4 different temperature, then you plot the log D versus 1 over T, then fitting that, you know the slope here, the slope will be equals to this one, right? E, migration enthalpy minus migration enthalpy divided by KB, then you can know the migration enthalpy here. And the intercept log D0, you also can get that because after fitting, you know the log D0 expressed like this, right? So we can get based on this result, we can get the D0 and the migration enthalpy term. Okay, so some people probably will, this is what we get from the design experiments, right? And you also can estimate the DI0 by checking the literature. You can check the possible migration entropy and the vibration frequency of your material. You can get this, probably you can get these parameters from the literature. And the latest point or latest constant part, you can measure that to get that, or you can check the literature to have a roughly estimation of this latest constant of this ion materials. Then because you know D0 is associated with this one, so as long as you got the latest constant, vibration frequency and entropy for migration, you can just substitute this term, then you can get the estimation of D0. Actually, this the value for this one is quite the data you measure for of D0 is similar, is very close to what you estimate based on some data published in literature. So it's quite close. The result is quite close, right? Okay, just give you some, provided you some ways to measure the D0 and migration enthalpy for your materials. Okay, so this is how we get the diffusivity for interstitial diffusion mechanism, right? And the method we provide here, the approach is to directly use the equation or results we derived from previous sections. But some people here we are going to give you the other approach by calculating the flux. So this method is the idea will be that yes, you can base on the fixed first law, the net flux equals to minus diffusivity concentration gradient. So by calculate or formulate the net flux, and you also have chance to get the diffusivity of this solute atom diffused through the interstitial mechanism. So the idea will be that. So here the other approach is by we are going to introduce to you is using the flux term. And first of all, how to formulate the flux? So we need to check by checking the unit. The flux can be expressed like the gamma, total atomic jump rate, times the area density C prime. The area density is the numbers of atoms per unit area. So flux, this is how we get the flux. So as long as we find the gamma and C prime, then you can formulate the flux, right? So this is the beginning, how we start this idea. So this is a BCC. So we do the same thing. We draw the simple cubic. We draw the unit cell of BCC. So it's like expressed like this, and we also label all the possible arthahedral interstitial site. And in order to formulate the flux and get the net flux, so we need to define two planes. Here we define the alpha plane and beta plane. So this will allow us to define the flux, right? So this is the alpha plane, this is a beta plane of the BCC. And we use the blue and orange cross to label different types of interstitial site on alpha plane, right? So this is, you can see the orange part actually is at the center face, and the blue cross actually is at the corner. So the idea to get the net flux in these BCC structures is we need to, first of all, we need to determine the direction of the flux. So we assume the flux is toward to right-handed side. There's a flux toward to right-handed side. So the net flux will be what? Equals to, as long as we get the flux from alpha to beta, then minus the flux from beta to alpha, then we can get the net flux to the right-handed side, right? So the idea is we need to, first of all, we need to get the flux from alpha to beta, then we get the flux of beta to alpha, then we minus this to this, then we can get the net flux. The idea will be that. So let's try to show you how to formulate the flux from alpha to beta. So alpha to beta. Based on the result here, we need to determine the gamma and C prime, right? So C prime is, start from the C prime. C prime is the area density. So we need to determine the area density of interstitial site in alpha or on alpha plane. So the area density, right? So this is on the face center. So if we consider area density for orange stuff is, we have 1, 2, 3, 4, 4 orange stuff and 4 orange interstitial side, and this is at the face center, so it's a 1/2, right? So 4 times 1/2 for orange interstitial side, and the blue one is at the corner, so it's we have 4, but each one is only considered as a quarter, so it's a 4 times 1/4 for the blue interstitial side. So in total we got 3 of interstitial side, and the area here is A times A, so the area concentration is 3 over A squared. So this is we deal with a C-prong, right? And next we need to determine the total jump rate. So now we need to determine whether all interstitial side, including the orange and blue, can make a successful jump to beta plane. If it can make a successful jump to beta plane, then that will contribute some flux, right? It will definitely contribute the flux. If not, then that kind of jump is not going to contribute to the flux. So we don't need to consider that in that case. So let's take a look on here. The orange, the atoms at the blue, this corner side, can these atoms make a successful jump to beta plane? No, because this is BCC, so there's definitely an atom located at the corner of this unit cell, right? So the atom at here cannot make a successful jump here, and also this atom cannot make a successful jump to beta plane. The same idea for this one and this one is not going to make a successful jump because there are atoms at the edge of this BCC. Some people probably consider, Professor, can this atom jump to here? No, because this distance is longer than A/2, right? Longer than this one. So first of all, we need to consider the nearest available site. And next week, so this for the atoms located at the blue corner side is not going to make a successful jump to beta. So this is not going to contribute to the flux from alpha to beta. Then let's check the atoms at the center face side is expressed at orange. So the atoms at this side is going to make a successful jump to beta plane, and with the distance A/2 is the nearest distance, right? So this one can make a successful jump, and this one can make a successful jump. This one jump here, and this one jump here. So the direction actually is the same, right? These directions for these two sides are parallel, so directions just one. So here, in order to based on this, we need to formulate the C-prong. Although the area density is here, but only 2 out of 3 atoms can make a successful jump to beta plane. So it's 2/3. C-prong can make a successful jump to beta plane. So let's try to formulate the flux alpha to beta. The concentration C-prong, only 2/3 atoms can make a successful jump to beta plane. C-prong 2/3 times C-prong. Related to the atomic jump rate, we only have one direction, so it's a 1 times gamma prong. As we mentioned, it's is just one directions to allow the atoms locate at phase center to jump to the beta plane, right? Okay, so we got the one direction times gamma prime, and this is 2/3 prime. So we got this results. And next, in order to, because finally we need to, we are going to compare with the results we derive with the fixed first law, right? So this is area density, but the concentration shown in the fixed first law will be the volume concentration. So we are going to try to convert this area density to volume density. Okay, so what we deal with, how we deal with this? So this is the area density, right? So we need to give it a volume, unit volume, to convert this area density to a volume density. So the better way to us to define give it a volume would be like what I drew here, because would be, and the length or the thickness would be A/2. Because within this unit volume, I mean this small volume, there's no more or additional interstitial size. If we increase, I mean if we increase, some people probably would say, oh, if you increase the A/2, enlarge that to this, but there's other interstitial size here, so you are not going to do that. So we can use this tiny volume to try to convert this area density to become a volume density. So the thickness of this volume will be A/2. So C prime and divided by A/2 thickness, then we can get the volume density or volume concentration. So here C prime will become C times A/2. So we use that we can get the flux alpha to beta can become here. And next step, we are going to get formulate the J from beta to alpha, right? So how to get the flux from beta to alpha? First things come out from your mind probably will try to do the same steps as we mentioned. You need to calculate concentration or area density and determine the numbers of possible jump directions, something like that. But here we provided the other choice. Here is we just play with modify the concentration here, become here. So then instead of get the area density and determine how many possible jump directions, we use this method to get the concentration of interstitial site at or on the beta plane is C. C actually is a concentration at alpha plane. Then we use the distance. This distance is A/2. This is A/2, right? And gradient, concentration gradient term, this is Y, so partial C, partial Y. Then we use this to get the expression of concentration of interstitial site on beta plane. Then as long as we get this alpha beta and beta alpha, so we can get the net flux can express like this. So after arrangement, you use this to minus this one, so the rest of part you got this one. Then compare with the fixed first law, then you can get the diffusivity of this interstitial atoms can definitely is equals to this term. So we got the compare this and this, you can get the results here. This result, and some people probably want to instead of use a gamma prime, some people probably want to converted to gamma. So you use the same Z equals to 4. Then A, some people want to convert it to R, so you can get the result here. The result actually is the same with previous slide we derived by using the equation, right? But this is the result will be the same, but the method is different. So actually, now you have some idea why we want to use this kind of expression of concentration of interstitial atoms at beta plane. Why? Because we want to have this concentration gradient term to compare with fixed first law. Then we can get this. You compare these two, right? Then you got this term is diffusivity. If we directly calculate the area density and possible jump directions, then you can directly get a value for flux beta to alpha. And after you use this term to minus this term, you are not going to have the concentration gradient term. So that's why we use this to get the to get the expression of concentration of interstitial atoms on beta plane. Okay, so probably I can draw something, and you can, and because some people ask about why we can use this kind of expression, so I try to based on this figure. So this is y, right? And if this is alpha plane and this is beta plane, and this is C alpha, right? This is a concentration. And why we can use this okay. So how to get the C beta? How to get C beta? Actually, this term is C beta, right? C beta based on this actually is C alpha plus what? It's dy. Here dy is the distance between alpha and beta, and concentration gradient along y, right? So this is A over 2 concentration gradient, and this is C alpha. We assume C alpha, right? This is C, right? C and A over 2 concentration gradient. So this is how we use this. Actually, this is C beta, right? And this is C alpha. Okay, hope you can. Okay. So I'm going, in order to make sure you really understand, so let's give you the other example is interstitial diffusion in FCC. So now we consider we have a FCC structure and have a lattice constant A. So it's so FCC. So first of all, you need to draw the unit cell of FCC, right? And the lattice constant is A. So it's A equals to B equals to C equals to A. So the lattice constant is A. The rate of solute atom jumping from one octahedral interstitial site to nearest octahedral interstitial site is R in the specific directions. So this tells you that the rate, so it's a gamma prime equals to R, right? Because in specific, gamma prime is atomic jump rate in specific direction equals to R. And the first question is, please answer, can you answer the solute diffusivity in terms of A and R? Solute diffusivity. So first of all, you need to determine, because now we know the gamma prime is R. So what's the Z? Now, if you focus on, because it is tetrahedral interstitial site, so you need to label all the tetrahedral interstitial site. And focus on here, we need to determine the Z. So the nearest interstitial site will be how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, it's 12. And the distance here, nearest distance, small r is the distance, is a over 2 square, a over 2 square, and take the root on it. So we become here, so you just substitute all the parameters here, then you can get the RA squared for absolute diffusivity. If there's an answer, and question B is, if there's a absolute concentration gradient along 1, 0, 0 direction, is a gradient along 1, 0, 0, derive the absolute diffusivity in 1, 0, 0 based on the net flux. So there's a flux absolute concentration gradient alone, so imply and tell you that there's a net flux along 1, 0, 0 direction. So can you formulate the absolute diffusivity? So as long as you know you need to formulate the flux, so you need to define two planes which is perpendicular to the flux, the direction of the flux, right? So we call it this alpha and beta plane. And in order to know can formulate the flux, you need to write it down. It's a gamma times the area density. Gamma is the correlation possible numbers of possible jump directions times the atomic jump rate along specific directions, and this is area density. So first of all, we need to determine the area density here. So area density for this interstitial size, you got 1, 2, 3, 4, 4 at the corner. So 4 times a quarter, and at the center, this one is 1. So you got a 2, and the area is a squared. So here you got a over 2 squared. And next, a over 2 squared here. And next, you need to determine the numbers of possible jump directions for these interstitials. So first of all, we need to check this one. Then we check this one. Okay, first we check this one. Possible jump directions jump to beta plane. So you got here 1, 2 is with same distance, 1, 2, and you also have here inside the monitor or display, right? So you got 1 direction, 1, 2, 3, and you 4. You got the 1 here, right? 1, 2, 3, 4. So for these interstitials, there are 4 possible directions. And let's check this one. Is 1, 2, out of the monitor plane. So 1, 2, 3, 4. Bottom and top is a symmetry, right? So also 1, 2, 3, 4. But these 4 are the same with this 4, right? 1, 2, 3, 4 is identical. And the same thing happened at this on this atom is also 1, 2, 3, and 4, and also 1, 2, 3, and 4. Each the interstitial at the corner have 4 possible jump directions, and these 4 directions are parallel, so we only have 4. Let's check for this one. 1, 2, 3, 4. Actually, also the same. Also 4 directions, the same directions for all these atoms. So actually, we have 2 atoms, right? 2, and everyone can jump to beta plane with 4 directions. So that's how it's a 4 gamma prime and 2 out of 2 C prime can jump to beta plane. So let's set results here. And as you know, this is alpha beta, and we change the C to expression like this. to express to get the expression of concentration of interstitial atoms at a beta plane. So use a 2C plus Y is A over 2 concentration gradient is along X. So minus got the net flux. So the same results here, the same when you got the same values for solute diffusivity as what you get in answer A, right? It's the same, right?